All right. Let's get started. So today we're going to be doing the first of two cryptography meetings. And yeah, let's get started. So just a couple of announcements. So Emma over here is starting a block picking support group Mondays, 8 to 9 p.m. Where is it?
It's but it'll definitely be.
Okay, the location is somewhere in Steeple. Just keep an eye on the Discord. We have logs, we have picks. So feel free to come and block pick stuff. Very fun. All right. In the long-standing tradition, here's a meeting flag. Enter it at SIGPwny.com. And here's a XKCD. You'll be fine. So like we upload the slides, and so you can get the flag later. I'll give you time to enter it now. Is anyone here not familiar with CTFSComponent.com? And needs help registering and stuff? All right, can someone? Yeah, go for it. Oh, are the meetings on? Oh my god. Yeah, hey Pete, I put the list, but can you just put her? Yeah. My bad. Whatever. In theory, by the time I'm done talking and you know everything, because we all when it takes the first time, the meetings will be up. The challenge will be up. But yeah. Without further ado. So I'm just gonna go over a couple of basics of what cryptography is. Then I'm gonna go over two basic symmetric encryption algorithms, XOR and Diffie-Hellman. All right. Also, here's the scoreboard. Might be a little bit hard to read, but it's really hard to read. The projector quality is really low for some reason. I don't know.
This has never been a problem before.
We're in 1280p goodness right here. Yeah, people are skyrocketing. Nearly 30,000 points is actually insane. But yeah, congrats to the top 10. And if you're looking to get more involved outside of just doing challenges, we're looking for people to help run meetings, plan social events, create challenges for UI, UCTF, fall TTF, and meetings. And just in general get more involved with the club. But yeah, please flag down any helper or admin if you're interested in getting more involved. We want to grow this club. We want to get more people involved. The barriers to entry are not as high as you think. Please feel free to get involved in any way possible. If you have ideas outside of this list, feel free to throw that to us as well. But yeah, what is cryptography?
Don't worry about that.
No.
Okay. So anyways, what is cryptography? So our two favorite protagonists throughout all of cryptography are Alice and Bob, and they want to talk to each other. However, the aptly named eavesdropper, Eve, wants to learn what they're talking about. And so the idea is we're going to send an encrypted message from Alice to Bob such that Eve cannot read it. Eve is usually the entire internet. And anyways, why do we care about cryptography? Why do we care about all this math? Who cares? Only these people. Anytime you see the S in HTTPS, that means using cryptography to make your web browsing more secure. Apple's been in the news a lot over various cryptography, privacy related things, any sort of password manager, the forbidden cryptocurrency, and the first S in SSH is secure, meaning you're using cryptography to connect stuff. So yeah, cryptography is very important. So what was cryptography before computers existed? Because that was the thing. So cryptography in ye olden days was using very simple patterns that someone could do by hand because they had no other option. So they're really hard and really annoying to break by hand, but the power of modern technology, you can break them in milliseconds. The classic example is the Caesar cipher, named after Julius Caesar.
Shout out Julius Caesar.
Shout out Julius Caesar. So The Caesar cipher is where we rotate every character in the alphabet by a fixed amount, by some amount k. So if you want to map A to C, B to D, etc., this is rot 2, and yeah, that's just what it is. You can generalize this to just a general substitution cipher, where you map every letter uniquely to a new letter that you can reverse. And however you do this, it's just called a substitution cipher. We're doing things character by character. There are many more examples. There's an example challenge on the challenge store about a visionary cipher. They're all extremely trivial. Hopefully by doing that challenge, you'll see why no one uses these anymore, except maybe third graders. So before I can actually get into cryptography, I need to talk about how computers represent data, and really how computers represent messages and numbers. So there's no real like unified format for doing numbers and messages in cryptography. It kind of all depends down to the challenge and down to the implementation. But I mean, at the base level, everything's binary. Any binary operations we can think of probably get used in some sort of cryptographical aspect. And there are many different ways of actually doing this. So the idea is you're gonna have to like look at challenge sources to see how the data is being represented, because you're going to be transferring between encodings of various sort. Like, is it a hex message? Is it just a really long number? Who knows? You have to look at a challenge source. I wish I could give a magic, here's what you do, but you can't, because there's no really agreed upon standard. I guess one tip is that cryptography people really like Python. And so in Python, there's a data structure or data type that's not really talked about in any courses, called bytes and byte strings. It's an actual object called a byte in Python. You're going to always want to be using these, not actually normal strings, because normal strings are ugly. So I'm not going to go over this table, but I've left this up on the slide about some really quick conversions to and from different formats. The slides are on the website, so don't actually bother trying to memorize this. But it's a really good cheat sheet for how, if you want to, in Python, convert between various different data types, so that you can actually do what you want. But yeah, I'm not going to go over this because no one's going to remember it. So anyways, we now know how to represent data in some way on a computer. So now, how do we actually encrypt things? And we're going to go over maybe the most basic of modern encryption. That's at even if it's not used directly, it's at the core of a lot of different algorithms, and it's XOR. So the idea is that we're going to want to do some symmetric. We're going to do some symmetric encryption, and the idea is that Alice and Bob have the exact same key through some means. We're not going to get into key distribution here, but the point is somehow Alice and Bob have the exact same shared key. And the key that Alice uses to encrypt her message is the exact same key that Bob uses to decrypt this message. So it's symmetric. It's the same way, same both ways. And XOR is a really simple operation. You look at it bit by bit. If you want to XOR two things, XOR is true if and only if one of the inputs is true. So if both inputs are true, it's false. If both inputs are false, it's also false. It's true if and only if exactly one is true. So it's like OR, but we only care about the exclusive part. Hence the name XOR. And XOR has some really nice properties that make it perfect for symmetric encryption. So let's say M is our secret message that we don't want the world to know. And we have K is our key. And so what we're going to do is we're going to let C be a ciphertext, the encrypted message, be M XOR K. So we're going to go bit by bit and XOR every single bit of M with the key, and we'll get some sort of output. So some really nice mathematical properties about XOR, which are going to allow you to actually break it in many cases. So one thing is that order doesn't matter. It's like addition. A plus B is equal to B plus A. Similarly, M XOR K is the same as K XOR M. And we can group these things as needed, right? You can throw parentheses and get rid of them, and it doesn't really matter. XOR away. If you XOR something with 0, if you go back to the table, it's not too hard to see that if you XOR 0 with 0, you get 0. If you XOR 1 with 0, you get 1. So XORing with 0 is the identity. And also, self-inverse. Remember that 0 XOR 0 is 0, and 1 XOR 1 is 0. So if you XOR something with itself, you're going to get 0 back. And the point is, this kind of behaves a lot like addition with a couple extra rules. And so we can do things like, how does Bob decrypt? Well, Bob has the same key, like I said, and we just take the ciphertext, XOR with the key, and you see, what is C? That's M XOR K. What's K XOR K? 0. What's M XOR 0? M. So Bob actually does decrypt the message as intended. And some basic attacks on XOR. So these are kind of going to be like a lot of the challenges you're going to see at like intro level. Like there's going to be like the easier challenges that you see at the CTF. So in general though, XOR is really hard to break. If it's called a one-time pad, because if all I give you is, hey, here's the ciphertext, it was M XOR K, and with no other information, you have really no better hope of guessing the key other than checking every single bit combination for K. So if you have a bit string of length lambda, then you're gonna have 2 to the lambda possible bit strings. And I don't got the time to try all of those. So usually in a challenge, we'll give you some sort of extra piece of information. So for example, maybe you have a known plain text and ciphertext pair. I say, hey, here's M1 XOR with K, and so here's the message, and here's the output ciphertext. How can you recover the key? Think about it. And once you recover the key, here's another ciphertext. Try to decrypt that, and that'll be the flag. Just known plain text ciphertext pairs, because of the undoing properties of XOR, are a very, very common crypto challenge. At a bit more of an advanced level, you can take advantage of certain things, like if you know your message is mainly English, you can try different keys and see which ones produce like the most English letters. And from that, generally build a key. It's known as cribbing, and I'm not going to go over it, but it is the thing that you know. This basically any sort of known information can help you break XOR. And sometimes you just need to know something about the key itself rather than the message. So if you know that the key is really short, you can just brute force it. You might not be able to brute force a 512-bit key, but maybe if it's only a byte, that's only 256 combinations, your computer can do that in an instant. So don't be afraid of a little bit of brute force. Also, if you know what the flag format is, this is a really, really common strategy. You know what the flag format is, and the key is not as long as the flag, well then you know what the first, say, 8 letters are in the case of SIGPwny. You know that the first 8 letters of the flag are going to be SIGPwny and an opening curly brace. So using that, you can find out what the key is, or at least the first portion of it, and go on from there. All right. That was our first symmetric encryption algorithm. You made it through. Anyone have any questions before I go on to Diffie Hellman? All right. So Diffie Hellman uses something called modular arithmetic. So in cryptography, numbers can get really, really big, really, really fast. And so we're going to use modular arithmetic to keep the size of our numbers in control. Computers are good at multiplying numbers, but they're not so good at multiplying really big numbers. If I give you 2 1,000-digit numbers, your computer's not going to have a fun time raising one to the power of the other. So we're going to use something called modular arithmetic, which is essentially we're going to take remainders after division as we do our arithmetic. And so as we do our arithmetic, we're going to keep taking a remainder over and over and over again. So if we're going to compute something mod n, as people say, that means every single time we do an addition or a multiplication or a power, raise something to a power, whatever, we're going to divide by n and keep the remainder. So you might be familiar with this by the little percent operator in basically every single programming language. That's the modulus operator. And see why it's so nice, we're actually going to do some really quick math. So suppose we're gonna compute this monstrosity modulo 101. So if we're doing something mod 101, we're taking remainder by after division by 101 every single time. We can make this first simplification. Who can tell me why these two lines are equivalent? Yeah.
If we're remainder of like 140 over 101 and 131.
Yeah, so 140 minus 101 is 39. So that's the remainder, and you can keep that around. And the same thing, 131 divided by 101, keep the remainder 30. So that's where that transformation came from. Now, similarly, why does this transformation work? Well, 102 divided by 101, keep the remainder 1. And what's 1 to the power of anything? Just 1. So that goes away. And I know how to add two numbers, and I'm sure you do too. And we're done. Now I'm a child. So why do you care about modular arithmetic? So as we saw, multiplying numbers, and you can think about it, taking exponents of numbers is really, really easy. You can just tell your computer to do that. However, there's a very core problem at the center of Diffie-Hellman and a lot of other cryptography algorithms called the discrete log problem. And basically, this is the same thing as taking log, like you're used to, but instead of actually needing to work with decimals, we now have to solve for an exponent modulo some number. So if I have a to the b is equivalent to x mod p, then I'm going to keep taking remainders after p. I'm going to take a raised to the power b, take remainders after divided by p, and get x. And I give you this number, and I tell you what a is. I want you to find b. This is normal arithmetic. You take the log, like just on any calculator. You're happy, you get some sort of decimal. But we're only working with integers, so no decimals allowed. We're talking modular arithmetic. So this is really, really hard. So it's the basis of many, many cryptography algorithms because we conjecture it to be one of the hardest problems to solve. We don't really have many better strategies in the general case, other than trying a to the 1, a to the 2, a to the 3, a to the 4, etc., 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 until our computers give out. So the way I like to think about the discrete log problem is it's a trap door. It's really easy to enter, but kind of a pain in the ass to exit. So for example, who wants to undo this? Who wants to tell me what n is if 2 to the n is equal to 79 mod 97? Come on, I believe in you. It's hard, right? Now imagine this with really big numbers. So I can tell you it's 15, and you can raise 2 to the 15 and take it mod 97, you'll see it's 79. Undoing that is really hard. So multiplication is easy, discrete log is hard. Entering the trapdoor is easy, exiting is really hard. That's the analogy. And so Diffie-Hellman is going to be another symmetric encryption algorithm, which is going to take advantage of this very fact that multiplication is easy, discrete log is hard. And how does Diffie-Hellman work? Well, another way to think about it is we're going to mix paint using numbers. So Alice and Bob are going to have some sort of common paint that they already know. And they're going to have a secret color. And what they're going to do is Alice is going to mix a secret her secret color with the common color, and so is Bob, and they're going to send each other the mixture. And then since now they have their shared colors, then they can mix Alice can mix whatever Bob gave her with her secret color, and so can Bob, vice versa. And they'll get the same common secret because all 3 colors went in, right? On the left-hand side, yellow, orange, and green went in, and we got brown, and vice versa. They have a common secret. But has anyone here tried to unmix paint? I didn't think so. So now we're going to paint by numbers. So we're going to let G be a public number that everyone knows. The world is allowed to know this, including Eve. And people call this a generator. And we're also going to have a prime P that's going to be our public modulus. So everyone in the world knows G and P. These don't have to be secret. Alice and Bob are each going to generate secret values, little a and little b respectively. These are going to be kept secret, but they're going to compute g to the a mod p and g to the b mod p. And Alice is going to send Bob capital A, and Bob's going to send Alice capital B, and sending these over the open internet, anyone can see what A and B are. But so then Alice is going to compute B to the A, capital B to the little a, and Bob's going to compute capital A to the little b. And flip that way, yeah. And believe it or not, they have the exact same key. Just by using a little bit of arithmetic, we can see that capital A to the little b is G to the little a to the b, which is G to the a times b, which is G to the b to the little a, which is capital B to the little a. So, you know, Alice and Bob now have the exact same value. So they were able to exchange keys. You have a? Are you? Oh, okay. So, what were we doing? We were taking numbers and we were raising them to a power, and we were assuming they're secret. So remember, discrete logic is hard. You just take that for granted. But can you really take it for granted? There has to be some catch. So you have to choose G and P if you want to do this. If you want to roll your own crypto, as they say, unrecommended. Small primes are really easy to brute force. Just like how I said earlier, about how your computer is good at brute forcing really small things. If you use small primes, there aren't really that many values mod p, right? If you have like mod n, the only possible remainders are there 0 through n minus 1. So if p is only like 13, it's 12 possibilities. Your computer can deal with that. So small primes are one common cryptography challenge. There are these things called oracle attacks, where you're given access to some machine that can leak information, and you can use this leaked information to try to figure out the secret key. Even if the primes look secure, the oracle somehow leaks something. And don't be afraid when you're solving cryptography challenges to get out a pencil and paper, go to a whiteboard, go to a chalkboard. Actually write stuff out. Trying to keep track of stuff in your head is a really, really bad idea. I think for any cryptography challenge, I think writing out stuff on a board or paper to keep track of your thoughts is a generally underrated strategy. We're going to get more into this next week, but there are notions of safe primes and unsafe primes. There are links on the slides if you want to click on them. But in general, you don't want primes where p minus 1 has a lot of factors. We're going to talk next week about how that's going to lead to a really, really easy attack. But if you want to look ahead, there are links on the slides. But yeah, if you want to actually roll your own crypto, you have to pick safe primes. If you're trying to solve a cryptography challenge, one very common attack is just looking at properties of the prime. And this kind of comes down to knowing just certain attacks and seeing which ones work and which ones don't. These usually rely on the prime being unsafe in some sort of manner. And then just, this isn't really cryptography, but it gets thrown into cryptography categories and details a lot. A lot of crypto nerds are just math nerds, and they like little puzzles. And so a lot of the crypto challenges are really just reverse engineering, but instead of reverse engineering a binary, like we'll see next week, you're reverse engineering math. So you might have to like solve some sort of polynomial system of equations. You might have to do something in your algebra. There might be some randomness at play where you're trying to, you're given a lot of something that's seemingly random, but it turns out that randomness doesn't really have an effect, or maybe the randomness isn't even random at all. There's another challenge like this on the challenge store called the Chart of Friends, taking advantage of this. It's not really a specific cryptography algorithm, but it is just undoing randomness. So it's a good example about how just because you see a random number generator in some source code doesn't actually mean that anything random is going on. So the strategy, like I said, just don't be afraid to start. Take advantage of your computers, your little interpreters, and try patterns. See if anything sticks out. Very often, those patterns that you find are actually the key to solving the challenge. understand why the pattern happens, you can reverse it and solve the challenge. And how do you actually do this? So I mentioned Python a lot. There's a nice add-on to Python called SageMath, which just takes Python and is batteries loaded with a bunch of math for doing things like fast discrete log algorithms, special cases, setting up ciphers. All of this is kind of built into SageMath and is really useful. PyCryptodome is kind of like the go-to Python cryptography library. So if you're going to do cryptography challenges, you're going to get very, very familiar with this library. Pwn tools, which I believe has already been covered in some meetings, but it's not only used for Pwn, as the name suggests. Very often your cryptography stuff is running off on some server where they're going to give you a challenge of some sort. It's been randomly generated. You're gonna have to live solve the challenge. You don't get to just sit your computer there over the course of 48 hours and let it brute force. So Pwn tools allow you to automate this attack because as much as they say, get your pen and paper out, don't actually do all this with pen and paper. Don't be afraid to Google and use Stack Overflow. Literally Googling how to crack Diffie Hellman with blah, 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 blah. Information has solved many, many challenges. And I bet that's how some people came up with their challenges. So Google is your friend. Installing a lot of the stuff is really, really annoying. So there's a link here to a crypto hack, to a Docker container maintained by this group of people called Crypto Hack. And this Docker container will let you set up a nice Jupyter notebook in your browser with all of this stuff pre-installed, and you don't have to deal with it because if you've ever installed anything with Python, you know it's annoying. Speaking of Crypto Hack, we have a lot of challenges on our challenge vault, but there's so much cryptography out there that I will never be able to cover, even if I did a cryptography meeting every single week. So go practice Crypto Hack. They also have a Discord. It's some of the nicest people I've ever met. Their only goal is to get people to learn cryptography. They're a super welcoming community, and their challenges are very great. So they're structured kind of like us, where their challenges are meant to be educational. They're not just hard for the sake of being hard. The point is to build you up. So I highly, highly recommend checking out Crypto Hack after you're done with our challenges. But yeah, as far as the next meetings, Crypto 2 will be this Sunday, and Sagnik will be presenting on some more advanced stuff that I kind of hinted at. So if you want to learn more about breaking prime numbers, Sunday's the place to be, time to be. And then next Thursday, and the Sunday after that are going to be the Pwn 1 and Pwn 2 series of meetings. Really, really cool stuff. You install Pwn tools, you'll be one step ahead of everyone else. So I highly recommend going to Pwn next week. But yeah, here's the long flag again. Did anyone have any questions? No? Everyone understood everything the first time? Of course. Why wouldn't you? No, okay, go back and review the slides. But yeah, thank you for listening.